Welcome to the Chemistry 209 Masterclass series. This series of lectures is intended to highlight the key concepts of introductory spectroscopy and structure. This lecture, Masterclass 3, discusses the quantum structure of atoms. In Masterclass 2, we saw that atoms have an infinite number of quantum states that can be described in terms of the principal and orbital angular momentum quantum numbers, and that these quantum states converge to the ionization limit. However, when we measure the spectra of atoms, we do not observe an infinite number of transitions. There are two reasons for this. First, in any ensemble of atoms, only a finite number of quantum states are occupied. This limits the total number of observed transitions, since with any transition we also transfer population from one state to another. Second, our quantum mechanical treatment of atoms shows us that only very specific changes in quantum number can occur during a transition. These are referred to as selection rules. For atoms, we find that the principal quantum number can change by any amount during a transition. The orbital angular momentum quantum number, however, can only change by plus or minus 1, and the magnetic quantum number must either remain unchanged or change by a maximum of plus or minus 1. One way to think about the origin of selection rules is to view a transition between quantum states from a conservation of angular momentum perspective. In an absorption or emission process, the total angular momentum must be conserved. First, recall that photons have intrinsic angular momenta and that the orbital angular momenta are quantized. We can then plot the magnitudes of the photon angular momentum and the initial and final quantum state orbital angular momenta in a head-to-tail vector sum diagram. Thus, we see that only very specific relative orientations of the three angular momenta are permitted owing to quantization, and that the orbital angular momentum of the final state must be that of the initial quantum state plus or minus 1 unit of angular momentum provided by the photon. Ultimately, selection rules originate from the need for a non-zero transition dipole moment. There must be a non-zero dipole moment during transitions because this provides the electric field in the atom or molecule with which the photon's electric field can interact. Mathematically, the transition dipole moment is the product of the initial wave function, the dipole moment operator, and the complex conjugate of the final wave function, integrated over all coordinates. For this integrand to be non-zero, it must be totally symmetric under all operations of the symmetry group. This leads us into a detailed discussion of group theory, which is beyond the scope of Chemistry 209. We will, however, be touching on aspects of group theory throughout the course, since much of the language of spectroscopy is derived from group theory. For example, consider the inversion operation denoted I. We can think of inversion as replacing the coordinates x, y, z with negative x, negative y, negative z. If we consider the behavior of atomic orbitals upon inversion, we find that s orbitals are unchanged while p orbitals change sign. In the density plot shown here, inversion of the p orbital would cause the yellow lobe to become blue and the blue lobe to become yellow, which means that the positive part of the wave function becomes negative and the negative part positive. A wave function that is unchanged following inversion is termed even parity, while a wave function that is changed is termed odd parity. It is apparent that as we incrementally increase the orbital angular momentum, the wave function parity alternates between even and odd. With this in mind, we can see that delta L equals 0 transitions must be forbidden due to symmetry reasons. For example, consider an S to S transition, which would occur between two states with identical inversion symmetry, resulting in a totally symmetric product of wave functions. Including the transition dipole moment would therefore result in a non-totally symmetric integrand, since the dipole moment has an odd parity due to the positive-negative charge separation. The use of symmetry arguments such as this can significantly reduce the necessity for brute force mathematical treatment. Let's come back up a few levels of detail and take a look at the spectra of alkali metal atoms. These species have one more valence electron than their nearest in atomic number rare gas, and that single valence electron occupies an ns orbital. But why is it that the ns orbital is lower in energy than the np or nd orbitals? In Masterclass 2, we discussed the idea of electron penetration and shielding. If we plot the radial distributions of the 3s, 3p, and 3d orbitals, we find that the 3s orbital penetrates closer to the nucleus than the 3p orbital, which penetrates again closer to the nucleus than the 3d orbital. As a result, an electron in the 3s orbital experiences on average a slightly higher effective nuclear charge than one in the 3p orbital, which experiences a slightly higher effective nuclear charge than an electron in the 3d orbital. Thus, we find that orbital energies depend on the n and l quantum numbers. If we consider the valence electron of the sodium atom at large distance from the nucleus, from the electron's perspective, the 11 positive charges in the nucleus are shielded by the 10 negatively charged core electrons to yield a total apparent charge of +1. However, because this electron occupies a 3s orbital, it has a probability of being located inside the core electrons, which means that the core shielding effect is reduced, and the 3s electron experiences an apparent nuclear charge that is slightly larger than might otherwise be expected. In terms of our energy level expression, we can correct for this effect of radial probability distributions by either replacing the nuclear charge with an effective nuclear charge for each electron orbital, or, equivalently, we can introduce a quantum defect parameter. Whichever formulation we choose, the correction simply allows us to describe the fact that the 3s orbital is lower in energy than the 3p orbital, which is again lower in energy than the 3d orbital. The energy level diagram on the left shows that the emission spectrum of atomic sodium is enriched by the fact that level energy is also dependent on the orbital angular momentum quantum number. The emission spectrum of atomic sodium is dominated by 4 spectral series, traditionally known as the sharp series, the principal series, the diffuse series, and the fundamental series. We now know that these emission series originate from orbitals with L equals 0, 1, 2, and 3 respectively, and in fact, these traditional emission series labels for atomic sodium are the origin of the S, P, D, and F labels for atomic orbitals. Level energies are also affected by the magnetic interaction between an electron's spin and its orbital angular momentum. Spin is an intrinsic angular momentum that is associated with quantum particles, and it has no classical analog. The closest classical analogy for spin would be a particle spinning on its axis, which in the case of charged particles, like electrons or nuclei, would result in the production of a magnetic field. In the case of electrons, we define a spin quantum number s and a spin projection quantum number m sub s. If the orbital angular momentum quantum number of an electron is greater than 0, the magnetic fields produced by the electron spin and by the orbital angular momentum can couple to one another to yield a total angular momentum, which we describe with the quantum number j. Since the spin, orbital, and total angular momenta are quantized, only very specific relative orientations are possible. Again, we can picture these orientations in a vector sum diagram. We can also determine which values of j are possible for a given LS combination using a Clebsch-Gordon series. Here we see that the allowed values of j range from L plus s to the absolute value of L minus s in integer steps. So, for a single electron, j equals L plus or minus s. The spin-orbit interaction gives rise to splittings in spectra which are known as fine structure. In this case, we see that an antiparallel orientation of spin and orbital angular momenta results in an antiparallel orientation of magnetic fields, thereby reducing level energy. Likewise, a parallel orientation of L and S raises level energy. These energy levels can be distinguished based on their total angular momentum quantum numbers, which, like L and S, also have associated projection quantum numbers. Here we must also introduce a new selection rule to define how values of j can change during a spectroscopic transition. The emission spectrum of atomic sodium provides an excellent example of the spin-orbit effect. The first line in the principal series is the 3p to 3s transition. Since the 3s level has L equal to 0, there is no spin-orbit interaction for the lower state. However, the 3p level, which has L equals 1, splits into j equals 1/2 and j equals 3/2 spin-orbit components. As a result, the 3s to 3p transition splits into 2 spectral lines. In comparison, the second line in the diffuse series exhibits a spin-orbit interaction in both the 4d and 3p states. Although we might expect the 4d to 3p transition to split into 4 lines, only 3 lines are observed owing to the delta J selection rule. At this point, it is becoming apparent that we have to account for several quantum numbers in our quantum state description. Atomic term symbols provide a succinct notation for describing the coupling between the various angular momenta in atoms. Term symbols contain 3 important pieces of information. The spin multiplicity superscript, which equals 2s plus 1, tells us the total electron spin quantum number for our atom. It also tells us how many spin-orbit components the NL state has split into. The central letter provides the total orbital angular momentum quantum number. S, P, D, and F correspond with L equals 0, 1, 2, and 3, respectively. For larger values of L, the trend continues alphabetically. The subscript J value gives us the total angular momentum quantum number, which tells us how L and S are coupled. As we will see later in the course, similar term symbol notation is used to describe molecular states. Atomic term symbols do not explicitly provide projection quantum numbers, which indicate relative alignment of angular momenta. The relative L and S alignment are, however, implied by J. It is useful to know that projection quantum numbers can take integer values between the positive and negative extrema defined by their associated angular momentum quantum numbers. Thus we see that there are 2s plus 1 possible values of m sub s, 2l plus 1 possible values of m sub l, and 2j plus 1 possible values of m sub j. Term symbols are especially useful for describing many electron atoms. The most common angular momentum coupling scheme that is used to describe atoms is known as Russell-Saunders or LS coupling. Within the LS coupling scheme, the spins of all electrons couple to yield a total spin angular momentum quantum number, capital S. The possible values of capital S can be determined using a Clebsch-Gordan series, which for 2 electrons yield the integer values between the sum of the 2 electron spins and the absolute value of their difference. Here we see that 2 electron spins can align to yield either capital S equal to 1 or capital S equal to 0. Similarly, the orbital angular momenta of all electrons couple to yield a total orbital angular momentum capital L. The values of capital L can also be determined using a Clebsch-Gordan series. For example, an electron in a d orbital can interact with an electron in a p orbital to yield total orbital angular momentum quantum numbers of L equals 3, 2, or 1. It is the total orbital and total spin angular momenta which then couple to yield the total angular momentum for the atom. Again, we can determine possible values of J using a Clebsch-Gordan series. If we take, for example, the case of L equal to 2 and S equal to 1, we know from our term symbol that this corresponds to a triplet D term. From the Russell-Saunders coupling scheme, we see that the spin-orbit interaction can split the triplet D term into triplet D3, triplet D2, and triplet D1 levels. But what about the other possible combinations with L equal to 1 or 3 and S equal to 0 that we could imagine from our example? Are all of these combinations possible, and can we comment on the relative energies of the associated quantum states? In Masterclass 4, we will explore the quantum structure of many electron atoms in more detail. See you next time.